So two steps. There's proof by Pythagoras that the square root of 2 is a distance. And then there's a proof by Euclid that this distance is not a fraction. So here's how Pythagoras was thinking. And this is real short and easy. Well, let me do it this. I'm trying to think how to make this nice. Okay. So if you make a square like that, well, what's the area of this little triangle here? You know, this little square on the coordinate grid, it's 1 by 1. You know, it's 1 unit in each direction. So this has an area of 1 square unit that I'm outlining here. And so this little triangle is half of it. So it's got an area of a half. And this has an area of a half, and a half, and a half. So that tells you, or told Pythagoras, this whole square has an area of 2. But then it's a square. I mean, the way you make the area of a square is you multiply the side, or a rectangle, the length of the side times the length of the side, length times the width. If you call the length of the diagonal here C, if you call it C, then the distance C has got to be, you know, it's a distance so that C squared equals 2. And then Pythagoras said that he believed that all distances have numbers. So then he says, okay, therefore, there must be a number that when you square it, you get 2. And what caused all the conflict was he could not resolve that with the idea, he couldn't have all 3 things. He can't say numbers are just fractions and every distance has a number, and when you square this one, you get 2. You know, it drove him nuts, you know? Okay. But that's where we are with Pythagoras. Now, Euclid. Well, before Euclid, I mentioned in the previous video, there was this student of Pythagoras who did a proof 100 years earlier, but it was lost. And a little article I read said they didn't think that this student would have done it the same way that Euclid did, because at that time they weren't thinking about factoring the way Euclid was. So I don't know. So this is not the first proof, but it's the easiest, most elegant, and it's the one that survived. So Euclid says, suppose this C over here is a fraction. And if it's a fraction, you can make it a reduced fraction. You can cancel out from the top and the bottom. He said if you have a reduced fraction, and when you square it, you get 2, this will lead to a contradiction. It's sort of, so the pattern of the argument's going to be sort of like, well, if it's raining today, then pigs have wings. Pigs don't have wings, so it must not be raining today. Right? It's modus tollens, reasoning pattern we learned about in the logic chapter. If this reduced fraction, when you square it, you get 2, then pigs have wings, but they don't. Okay. So how are we going to get our contradiction? Well, so it's this reduced fraction that when you square it, you get 2. So m squared over n squared is 2. So m squared is twice as big as n squared. So m squared is an even number. So what about m all by itself? Is m even or odd? If you take an odd number times itself, you get an odd number. You know, because like if you do 7 times 7, you can't get anything even because there's no 2 in there. You know, to be an even number, there'd have to be a 2 as a factor, and it's not in the 7, and it's not in the other 7, so it's not in there. You multiply 2 odd numbers, neither one of them's got a 2, so when you finish multiplying, there's still no 2 inside. Okay, so if m squared is an odd number, if m squared is an even number, then m itself is even. Okay. So if m is even, so m is 2 times something. That's what even means. So m squared is not just even. If you multiply m times n, it's m times n. It's 2 times something. That's m times 2 times something. See what I mean? M squared is a multiple of 4. Your eyes are starting to glaze over. You say, where's this going? I'm almost done. It's 3 more lines. But see, if m squared is a multiple of 4, then half of m squared is a multiple of 2. See, n squared, it's half of m squared. So n squared is even. Almost just 2 more lines. If n squared is even, so n is even. Look at that. If you got a fraction, you square it, you get 2. If that distance squared equals 2, and it's a fraction, then the numerator is even, and the denominator is also even. So m over n is not a reduced fraction. See, all these numbers like a half and 2/4 and 3/6 and so forth, they're all the same number. You can write it this way just as well as you can write it that way. But anything you write in a reduced form cannot be this c. Any fraction can be written in reduced form. And when you do that, it cannot be the number c, this diagonal distance. It'd have to be some kind of a, if it's going to be a fraction, and if it's going to be a fraction, it can't be one. So that's the proof. Whatever it is, it's something else, not a fraction. So it was not like instantly acceptable. All right, we've got a new kind of number, but you can solve all these algebraic equations if you just go ahead and use it. So it's like a lot of these numbers where people were driven to just use them, and they weren't sure whether they believed in it or not, but what the heck, you can build your temples, you know, you can figure out how long it is across something, and so it's not a fraction, so you get lots of digits, and you can't can't exactly work it out, but you can get it so close it doesn't matter. You know, it became useful before it became accepted. And so that kind of sets the pattern for continuing extensions of the number system. I'm going to stop this one. And I'll do one maybe online or maybe just record it. But you'll have some homework on the complex numbers coming up. And so there's one more to do.